Okay, welcome back everyone. So today we are going to start another project series, and this project series is also going to be looking at particles, but with a very different take from our last one. So we're going to be looking at dynamic particles controlled with attractors. So let's take a look at where we will end up, and that is a particle system that looks something like the one in front of you. This particle system is going to be shown with some perspective view. We're going to throw some post-processing on top that's going to lead to this kind of cool tilt perspective that we have here. We're going to be able to add some interesting feedback techniques, such as these trails or some sparkles, kind of floating ethereal lights. We will also look at things like adding vertical velocity and perspective to our particle system. If we crank up the feedback a little bit, some of the trails start to look pretty cool as we have some vertical velocity in our system. Then, one of the most important things is going to be adding some attractors to our system. And these attractors are going to let us control this particle system in a way that is very finely tuned. And this is going to let us really have some really cool effects that are created without really needing a ton of extra work or network complexity. And the way that we'll do that is actually by working with a network of autonomous agents that are actually going to be rendered as our attractors and then used as attractors in the particle system. So that's what we're going to be looking at today, specifically how we can create this autonomous agent simulation and then use that in our next tutorial, or a later tutorial at least in this series, as the attractors for this particle system. Now, the last thing that we're going to do is look at how we can get Connect involved and be able to have some Connect controlled interactive attractors as well. So you can see that here, and we can see that these are working kind of in concert and in addition to the autonomous attractors. So this is going to be another way to just add some really cool interactivity and tons of possibility to your projects. So we'll get into all of that and some more over the subsequent tutorials. I think there's probably going to be somewhere like 4 or 5 in this total series. And we're going to leave the particles here today because what we're going to be looking at for the rest of this, as I said, is how we can actually create the system of autonomous agents that we will be using as our attractors. So I'm going to create a container. I'm going to call this container autonomous agents, and I'm going to jump inside. Okay, so what do I actually mean by autonomous agents? What I mean by autonomous agents are agents, in this case just little spheres, that behave, that have behavior that is defined by an algorithm that, once set up, is run with limited input. So we're not telling these agents where to move each step, we're telling them how to move and giving them some rules, and then turning the agents loose and letting them play in our sim. So, to give an overview before we actually start building this ourselves, we're going to be using a very standard GLSL simulation structure that's using a GLSL top to take in position data, velocity data, do some calculations, output position and velocity data, and then use the position information as instance coordinates for a rendering network. I'm sure most people have seen some version of this before. So if so, this part may be a bit of review, but I always find it's really helpful to just have reps creating these simulations to get really good and have some of the tricks kind of develop into muscle memory. If you guys haven't experienced simulations or created anything with GLSL as kind of the main engine in the past, that's fine. This is going to be moderately involved GLSL code, but it's not going to be crazy, and I will explain everything very clearly, I hope. So, do not be too worried, and with that said, now we can jump into creating our own. So when I get to the blank screen, I'm going to start by simply recreating the framework of this network, kind of the overall infrastructure, and then we will jump into the code right after that. So back to our empty container, I'm going to drop down a GLSL multi. I'm going to call that sim. I'm going to grab two nulls. I'm going to call one null pose in and another null velocity in, and that's because we're going to need both a position and velocity, as we just looked at. We can grab a noise top and just wire a noise top into each of these. And then we can have a null output. Actually, I'm not going to drag and drop that. I'm going to use a render select and then drop my sim onto my render select and change this camera buffer index to 0. This is purely aesthetic. It's the same as having a null, but we're going to use another buffer for our velocity later, and I like the visual setup of having the render selects instead of the null. So do what you feel is right there. Alright, so I'm going to turn this monochrome off. I'm going to open up my GLSL pixel shader and get it over on this screen. I'm just going to make one quick change right now, and that is to output my color. Minimize this. This is just his C thing, so we're going to be making a bunch more changes there in a second. What else do I need? I need a sphere. I'm going to set the radius of this sphere to something like 0.3. Change it to a polygon. Then I'm going to right click, drop a geo, drop a camera, drop a light, and drop a render. Then Alt N to add a null, and now we can see our instances being rendered, or just one of them for now because we need to turn on instancing. Rename this render select as pose data out, and then use Alt N to drop another null, which I will just call pose inst data. And this will allow us to keep things very clean and clearly labeled. Now I'll take my pose inst data null, I'll drop that on my translate and set the values to R, G, and B. R, G, and B. Now we have a lot of spheres. Make it a little bit smaller. We still have a lot of spheres, that's okay. We are going to address that in just a moment. But we're getting very close to having the overall framework of this ready to go. The last thing that I'm going to do is drop 2 feedbacks between each of the noise tops and the null top for the inputs to our sim. Call this pose feedback and call this vel feedback. Oops. Now, since I'm already in my autonomous agents, top, I'm just going to customize the parent component and start parameterizing. So I will drop my reset pulse from my pose feedback. I will then grab that parameter, drag and drop it with the expression onto the other feedback. I will then go up a level and create my link to my local comp, op.local.par.pulse, .eval. As I have mentioned in prior videos, and also have a specific video out now on this topic, I use a component with a global op shortcut to call it local, and then I have a pulse parameter on that component that I just reference everywhere in my project, that I have a pulse to make things really easy for me to reset. So now I can just press 1 no matter where I'm at in my network, and that will pulse everything for me. You can find that video here, and I recommend you take a look at that if you haven't yet. Okay, so now our structure is pretty much there, so we can start making some modifications. I'm going to just kind of move my visualization over a little bit, and the first thing we're going to do is set up a way to define the number of balls or agents in our sim, and then use that to set the resolution of our tops. So I'm going to call this parameter number of agents. I'll make that an integer. I'm going to default it to 20. You can make the range whatever you like. The reason I picked 20 is because that's not not an even square, so it will be a little bit more interesting for us to figure out what the dimensions are. So the way that I'm going to calculate our dimensions procedurally is by creating this quick little utility. I originally got this utility from David Braun, who has a shared TouchDesigner network on GitHub. This functionality was in there. That's how I found it. I've since kind of tweaked it a little bit to use in my own projects, but definitely wanted to mention the original because it is super, super handy, and just a repository that I recommend everybody go through, because he got some black magic in there for sure. So, just looking at one of those pieces of black magic right now, we're going to take our parameter chop. We're going to just grab the number of agents. I'm going to put a null next to that, and then I'm going to add a script chop. Now, a script chop, if you haven't come across it before, is pretty cool. It essentially just lets you use Python to create and alter the contents of chop channels. So if I edit this, we can see this is the default boilerplate. All we're going to be working on is our onCook callback, because this callback is what happens every time the script cooks. And to calculate what our resolution is going to be, we're going to read in our number of agents, and we're going to do some simple math to calculate what a width and height texture size would be, to be able to easily have 1 pixel for every agent, and then have that update every time we change our number of agents. So we can do that with the following. First, we need to add some channels to our script chop. So I'm going to say script op.append chan, res x, and then you can see this resolution just appeared right here. I'm going to do the same for my res y. Oops, for my res y, geez. So now we have our two channels. I'm going to say num agents is equal to script.inputs, the first input, and so inputs is going to be a list of input operators. So grabbing open bracket 0 close bracket will grab the first entry in that list of inputs, which is going to be this null. And then we can additionally use an open bracket 0 close bracket to grab the first sample from the first channel in this input. So this will evaluate to 20, and if I debug our num agents, we can see that the value of our number of agents is 20, as we would expect. By the way, debug is just like print. It is a TouchDesigner specific function in Python, and the benefit is that when you print, it will not only print your value, but it will also tell you what operator the command to print came from, which can be helpful sometimes when you're working with complex networks. So anyway, now we have our number of agents, and now we need to figure out what our dimensions can be. So I'm going to call a new variable, call that s, math.floor, open parentheses, math.square root, sqrt, of our number of agents. Floor is just going to round down to the nearest integer, so we're taking the square root of our number of agents, rounding that down to the nearest integer, and then what we're going to do is create a loop with for I in range, and then we're going to start with our square root. We're going to have our range extend from the square root value to 1, and we're going to step through that range using value step sizes of -1, which means we'll start at s, then we'll go to s-1, s-2, s-3, so on and so forth. Now what we're going to do for each of those values is say if our number of agents modulo I is equal to 0, and what this means is basically if our number of agents can be evenly divided by I, then we know we have a number that's going to factorize our number of agents and leave a clean remainderless value as the result of the division. For example, let's think about the best way to do this. If I go here and I just type math.square root of 9, it returns 3, as you would expect. If I do square root of 20, we get 4.4. So then, if I do math.floor, math.square root of 20, this will round this down to 4, and that means that our loop is going to start at 4. Say if our number of agents modulo 4 is equal to 0, well, 20 mod 4 is equal to 0. So if that means that we're going to want to set our width equal to 4, and then we'll set our height equal to the number of agents divided by that width, since we already know that division is going to result in an integer, because num agents modulo I is equal to 0. So that is super handy. Those are our two dimensions then. All we need to do is add them to our channels by using script.op open bracket res x in single quotes. That's going to be for our channel name. And then we're going to need to access the first sample of this channel using open bracket 0 close bracket. And we'll set that equal to our width. We will then do the same with the res y channel for our height. Now you'll notice that our script op is outputting 0 for resolution X and 10 for resolution Y, but we already, during our kind of example calculation, arrived at the answer that we should be getting 4 for our width and 5, or 20 divided by 4 for our height. The reason that we are getting 2 and 10 is because we are not stopping the for loop when we get a solution. So we're actually going to be grabbing the last solution because this for loop is going to keep going unless we add break. And this will just tell our code to exit the for loop once this condition is met, which will happen when we find a set of dimensions that are going to work for us. Cool. So that is everything on that front. So I'm just going to now drop a null, call that text size. I'm going to select my null in this script. I'm going to collapse that to a component. And then I'll call this component calc text size. So now we know what size our textures are going to be. So I'm going to go to my GLSL. I'm going to change the resolution to custom. And then I will drop my dimensions from our calculate compact text size to our GLSL. I'm also then going to drop that onto our noise that we get our first positions from, and I'm going to do that as an expression just for cleanliness sake. And then I'm actually going to get rid of this noise and use a constant instead, a constant top. And we'll set that equal to, we'll set this value equal to 0, and that will just give us 0 velocities to start. And then last thing we have to do is change our constant resolution to be our text size. So now, if I open our parameters, we are able to use this dragger to change the number of agents in our sim, and our GLSL resolution is changing as we go. The one weird quirk is if you try to use a prime number, it's just going to evaluate to 1 because there's actually no number I such that n mod I equals 0 for prime numbers, except for I equals the prime number. That's by definition what makes a prime number prime. So the only limitation to this approach is use something that is going to have a factorization. Cool, so that is our basic setup. And from here, all we have to do is change our GLSL code a little bit to give our agents some life, and then we will be cooking. So before we get started with that, the last thing I'm going to change on our kind of infrastructural setup is add a color buffer for our velocity output. So right now, we're just outputting our position. Like I mentioned, this is the same as if you just add a null and drag it out of the GLSL. But we do have the ability to output multiple textures from a single shader. You can do that using this number of color buffers parameter on the shader. The maximum number here is going to be limited by your GPU. You can see that yellow warning appears when I go from 8 to 9, and that's because my max color buffer outputs is limited to 8 when using pixel shaders on this GPU. So everyone is going to have slightly different figures for what your maximum buffers are, but we only need 2 for today. So again, just the way to think about color buffers are textures that your shader is going to output that you can then use later. This is super handy for so many use cases. but especially handy for simulations because we might want to put out many things, such as our agent position, agent velocity, maybe rotation, or some other data about our agent, lots of different things, and you can handle all of them very elegantly using these texture buffer outputs. So since we have added another one on our GLSL shader, we can just drop down a render select, drag and drop our shader onto it, and we'll see that our buffer index is set to 1, which, because color buffers are 0 indexed, means that that's the second buffer, and this one, our position data, is the first buffer. So I'm going to call this vel data out. And now I will show you in GLSL what we need to do to actually be able to set up that buffer. So since we're going to be working with our shaders quite a bit, I'm going to set up my workflow a little bit. I'll split this top and bottom. I'll make this a text port, and then I will drop my nope, there we go. I will get my info dat and say view contents in text port. Awesome. So you're probably used to seeing this setup when we drop down a default GLSL. This outvec4 frag color is setting up a variable that we set equal to some vec4 using td output swizzle, and that's what determines the color of our output. But as we just learned, this really just determines the color of the first output texture in the color buffers. What if we wanted to set the second color buffer output to be something different? To do this, we just have to add a little bit of code. So to this line, we're actually just going to add, well, I'll delete this line totally. And we will replace it with layout, open parentheses, location equals 0. So that's telling us, or that's us telling the GLSL compiler which output buffer we are laying out at the moment. Then we say out vec4, and we call it whatever we want, in this case, frag color. So now you can see how we're working again. It's just like we had originally. If I just get rid of that, we see nothing changes, and that's because, again, this is still just all for our first, all for our first color buffer. So to add our next one, we can just copy and paste this, change the location to 1, and then change our out vector to something else, like ovel. I'm actually just going to call this one opposed while we're here. I'll change that frag color reference to opposed. And now, if I write ovel equals td output swizzle vec4 of 0, we can see that our second buffer output is outputting all zeros. We change this to 1, we can see in here that we're outputting all 1s now. As a side note, this can also be pretty useful for something like debugging GLSL, which is obviously not the most easy thing to do in the world, or maybe not obvious, but it's not the most easy thing to do in the world. So sometimes I will create a color buffer and output something to it just so that I can have a visual and numeric kind of view into what calculations are going on. So for example, if I wanted to do something like float a equals opos.x times opos.y, and then I wanted to say, oh sorry, not opos, I should probably use color for this. and then color.r equals a. I don't know. This is obviously kind of a meaningless little exercise, but my point is, sometimes when you're doing this, maybe you're not getting the results that you're expecting, and you're like, okay, well, there's compiling, there's no compile errors, I don't really know what's going on. You can use a output buffer like this to output A, which in our case is an intermediate value that we actually don't see at all in our output, and use that to explore the intermediate level calculation results, which can really help in figuring out what's going on, especially if there's some problem that seems like there's no good reason or you've checked everything. This can be super helpful. So just wanted to call that out. I'm going to change this back to ovel. Change this back to ovel, and then we can just leave that for now. We should drop our pose data and vel data onto our feedbacks so that we actually have our feedback loop working. And now we go back to our code and we can start to build up to our agents. So one thing I'm going to do first is define pose as just the number 0 and define all caps vel as the number 1. This is just going to be defining input texture locations, which will allow us to easily reference those input textures elsewhere in our code. Now I'm going to make what is called a struct, and this is just a simple data structure inside of GLSL. You do that by declaring with struct. I'm going to call it agent. Unlike a lot of other programming languages, you don't have a initializer with arguments or anything. You just have a open curly bracket, close curly bracket, and then inside you list the data that our structure is going to hold. So in our case, that'll be a vec2 called pose and a vec2 called vel. Now we'll make sure that you close the struct with a semicolon. And that should work. And now we can see everything is working here. And we have a structure called agent that we can then work with. For an example of how to work with a structure, we can actually use it very similar to any other velocity type. So I will make a function that will return a type agent. I'll call that read agent, open close parentheses, open close curly brackets, and we will create a variable called agent. We'll name it A. We'll say our a.position is equal to texture std2d inputs. Now instead of using 0 like we would normally do, I'm going to use uppercase pose because that is going to be replaced with a 0 during compilation due to this define statement here. And then we can just grab vuv.st for our lookup location and the rg values of that vector, since our position member of this agent is a vec2. Then I'll say a.vel is the same thing, but instead of grabbing the position texture, I will grab the all caps vel texture, which will be the first one. And then we can just return our agent A, and now we have a function that will create an agent struct, read it and fill it with data, and then give it back. So now we can go to our main. We can say agent me is equal to read agent, close bracket, and then we can say our color, since we don't have that variable anymore, get rid of it and replace it with a vec4. That vec4 will have the first two components of me.pose, and then we'll just give it a 0 z component and a 1 alpha component. we're getting an error because we still have, we're referencing this variable a by our line assigning a value to oval, so I'm just going to get rid of that for now. And we can see that now we are indeed reading in our position texture and outputting our velocity texture. Or sorry, reading in our position and velocity, and then right now just outputting our position. But if we did our position output as our old position plus our velocity, and then reset this, we can see that we're starting to get some motion, which is definitely good, but not quite there yet. So the reason that we're not quite there yet is because we're actually not outputting our velocity at all. Since we deleted that, all we're doing here is basically just saying read in the agent, output the position, everything else stays the same. So let's create a function, a void function. We'll call that update velocity. That update velocity is going to take in an agent called A, and since it's void, it's not going to return anything. All we're going to do is actually, right now, write out our output velocity by setting our oval variable equal to td output swizzle. We'll pass a vec4 constructor through there, and in our vec4 constructor, we will pass a .vel for our xy components, and then a 0 for our z, and a 1 for our alpha. Now all we have to do is call update vel, and pass me into it in our main loop. We can see that our shader is compiling successfully, and we have the majority of our kind of code framework all set up. So from here, we can start to refine things a little bit and add some actual agent behavior, so it's not just them sitting statically here on the screen. Alright, so the first behavior that we can do is have our agent just seek the origin. This is super helpful because you're generally going to want to have all of our agents stay kind of in the range that our camera's pointing at. So having some behavior like seeking the origin is helpful because it will keep everybody kind of close to the center without requiring too much additional programming and hard coding in of rules. So one thing I forgot to do is just turn my offset to 0 and make sure I have 32-bit float for this noise. I should also set my GLSL to 32-bit float and make sure that my velocity constant is also a 32-bit float, so that I have a 32-bit float value for everything. After I reset, we can see that now my particles or agents are centered as we would want them to be. Now nothing is moving because we're just reading in a 0 velocity, and then nothing's happening because there's no velocity to update the position with. So let's add our seeking the origin function and get some velocity. So I'm going to say create a function called void seek origin, open parentheses. This function is going to take an agent A in. We will need, before we can go further, a uniform. Uniform vec2 u origin. This is then going to be a variable that we can set on our shader. I'm going to make sure that's set to 0, 0, so our origin is the center of the screen. Then in our seek origin function, we can define a new variable. That variable is going to be a vec2, and we'll call it dir and set it equal to the position of our agent minus the position of the origin. And then we will adjust our velocity. So adjust the agent A's velocity by subtracting the normalized direction times, and then here we need to add a couple more uniforms. One of those is going to be u delta, which is going to be our time step. That'll be 1 over me dot time dot rate. We can add it here with uniform float u delta. And then I can add that multiplication here. Close it with a semicolon. Reset my simulation. And then in our update vel, I'm just going to call seek origin and pass our agent A through it. And then we can see what happens. So nothing is happening at the moment, and that is because we're not actually saving our modifications on our agent. So you can see there, all I did was just add this in-out classification or type to our input variable. And what that means is that anything that happens inside this function is going to be applied to the variable it's passed in, and that variable is going to persist after the function. So the changes will persist on that actual instance, I guess. So basically, when we don't have in-out and we just have seek origin, there's nothing that's specifically saying the agent that we're applying this function to is the same agent that we are kind of referring to through the rest of our code. Using this in-out will make that relationship explicit. So we can also add an in-out here to our update velocity. And now we can see that we get a lot of motion, and we are also seeking the origin as expected. And that is because by including this in-out, we're saying, okay, we're passing the agent me through the update vel function. That me is going to go in to the update vel function. It's also going to come out with all of the changes applied. In the update vel, we're doing the same to seek origin, so we're passing in an agent and we're taking the same agent out, and then those changes are going to be saved as well. So a handy delineation that will help when building sims. Now, our agents are going crazy over here, and we probably don't want them moving that fast. So a couple things that we can do to pull things in a little bit. One is add a u screen space step parameter, and we'll add another parameter called u origin bias. Uniform float u origin bias, uniform float u screen space step. And then we can additionally multiply our adjustment to the velocity by these two numbers or parameters, which will allow us to then have some more fine control over our particle behavior. So u delta is, like I said, a time step, but we might want to have that time step not be one-to-one with screen space steps. For example, if we're using a very wide world space, like thousands and thousands of units across, we might want to step more than one unit in world space per frame. And so this adjustment is going to let us tweak that. And then u origin bias is going to be a parameter that we apply only to this seek origin function that will allow us to define how strong the force of attraction from the origin is on the rest of our particles or agents. Finally, we want to have a u max speed parameter, uniform float u max speed, and use this to limit the speed of our agents, just so that they don't get too crazy. This will give us a way to limit the speed. So to do that, this is very easy. We'll say if the length of our a dot velocity is greater than u max speed, then what we want to do is set our a dot velocity equal to the normalized velocity times the max speed. So basically just limiting our speed at its maximum, and we do that before we output our new velocity. And so if we turn our max speed way down, we can see that this also will impact how much our particles or agents are able to move. So now we have quite a bit of control already. Something else that will become apparent if we set the bias for the origin equal to 0 is that our particles are just going off screen. That is, well, not super helpful. So we should probably add some world bounds to our sim to keep everybody in line and kind of in the same area. So we'll add another function right underneath seek origin. We'll call that void avoid world bounds, and this will take an in-out agent A as well. We'll have to set up some uniforms, so we will need our u world bounds to actually know what the world bounds are. And actually, I think that should be it. So we can just add that uniform, a uniform vec2 actually, u world bounds, and then in our avoid world bounds function, we can say something like this. We want to not look at where the agent is, but where they're going. So we can create a new vec2 and call this projected position, or projpose, and set that equal to our a.position plus normalize our a.velocity, multiply that by our u delta, and then multiply this by our u screen space step. One thing that I should definitely do is multiply our output position adjustment by the same u delta and u screen space step. I forgot to do that earlier, but definitely should have. And now we can see that my motion is going a lot slower. And as I turn down my max speed, we're going to 0. And as I turn up my max speed, we can see things are moving faster, but increasing the screen space step is what will take to really make them move faster. Alright, so now we need to finish off our world bound avoidance. We'll say if our projected position dot x is less than u world bounds dot x, or if our projected position dot x is greater than u world bounds dot x, we will want to take our x component of the velocity and just reverse that by multiplying by -1. And I actually want to make sure that our projected position x component is less than the negative x component of the world bounds. I can just copy and paste this down here and just simply change my x's to Y's. In VS Code, if you just hold down Alt, you can do alternate or a bunch of different cursors, which is super helpful. Yeah, so now I'm avoiding my world bounds. If we change our world boundaries, we can not see the impact now, but if we add it to our update velocity function and actually apply it, then we should be able to. So as we can see, there's something happening. I think the reason that it's not working completely is because we're actually starting some particles outside of those world bounds. So I will make this start amplitude for our position much smaller, so everybody starts in the center. And then if we play with our world bounds, okay, sorry about that. So the reason that we can't see this working is actually because we don't have enough velocity going at the moment. So if I just copy and paste this noise, crank up the amplitude a bit more, wire this into our initial velocity, we can see our world feedback is now working, or sorry, our world bounds are now working. And if we make it smaller, we can see that our particles or agents are increasingly constrained. And by increasing, we can allow them some more space. And then here we can just, see all of these agents bouncing off of the walls, which is also pretty much what we desired. So this is getting there, but this is somewhat chaotic, and I'm not sure. Maybe move these, make these a little bit bigger. Somewhat chaotic, and what I would really like to do is have these agents avoid each other, so that there's not all of this chaos, and the motions are a little bit more well defined. So to do that, I'm just going to add an additional function that will apply to our update velocity. I will call that void avoid agents, and this we will also do a in-out agent A as the argument. Before we move forward here, I'm going to add a couple more uniforms. One is going to be ures, which I'll set equal to me.width. It's hard to see. I will set equal to me.width and me.height. We will then have a u avoid threshold and a u avoid distance. Let's just add those uniforms here. A uniform vec2 ures, uniform float u avoid threshold, and uniform float u avoid distance. Now that I have these parameters, we can go back to our avoid agents function. What we're going to do is create a double for loop to loop through all of our agents. We'll do that by using for float I equals 0 spot 0 semicolon I less than ures.x semicolon I plus plus open and close curly brackets. So that's our first for loop. Our second for loop will be right inside of this. For floats j equals 0 spot 0 semicolon j less than ures.y semicolon j plus plus open bracket and close bracket. So now we have a double for loop starting from I equals 0, j equals 0, and going up to our res in each direction and incrementing by 1 each time. To figure out where we need to sample our texture to get our agent, we will create a UV variable that is a vec2. We will set that equal to a vec2 using our I and j values for this iteration of the loop. And then to those, we will add a vec2 that has 0.5 in each component. And what that will do is simply grab the middle of each pixel that we're sampling. Now, to get into our 0 to 1 range, we just have to say UV divided equals URes, and that will convert to our 0 to 1 range. So now that we have that, we can create a new agent and call that other, and use our read agent function, which we'll have to modify slightly to take in a vec2 UV and read in based on that vec2 instead of using our vuv.st in this function. That means we can then put our UV right here, and the last thing we'll have to update is simply pass vuv.st into our read agent function in our main call. So now we're reading in our agent data for every other agent, and all we have to do is say if our agent, our other agent, is too close to me, then I'm going to move to avoid him. So we can do that by creating a vec2 called dir that will be set equal to the position of the other agent minus the position of our active agent. And then we'll create a variable called dist that will be equal to the length of our direction, and that's going to be how far away they are from each other. If our distance is less than 0.001, i.e. very, very small, or if our distance squared is greater than our avoid distance squared, then we're just going to continue. And that means move on to the next iteration of the loop without doing anything. The reason we're doing it for these two criteria are because if our distance is very, very small, that means most likely the other agent is the same as our active agent, so we obviously don't want to do anything there. And the other component of this is if the square distance is greater than the square of the avoid distance parameter. We're squaring so that there's some nice fall off, but in theory you could use a linear measure and just do distance greater than you avoid distance. I like it a bit better using the squares here. So if the distance squared is greater, that means they're too far away to need to avoid, which is awesome, and that's why we're passing or continuing through our loop in either of those cases. However, if these cases are not true, it means that our distance between the agent, active agent, and other agent are too small, and we need to move to avoid. To understand how much to move to avoid, we'll create a float called %, the PCT, and we will calculate the ratio of our squared distance to our squared avoid distance. Then we will set this % equal to our threshold, avoid threshold, divided by the % value minus 1. Now, if you think about it, this PCT is always going to be some value less than 1, because to get to this part of the evaluation, we know that the distance squared is less than the denominator, so we know that this is going to be less than 1, which means if we have a avoid threshold divided by something we know is going to be less than 1, the result of this is going to be greater than 1, so we subtract 1 from it to essentially convert this to a kind of like an overflow value that we can use to apply in our next line, which is going to be our application to our velocity. So a.vel minus equals, at this point we've done it several times, normalize of our direction, which again in this case is the direction from the other agent to us, and we'll multiply that by our u delta and by our percent, and then by our screen space step. Now, if we simply call avoid agents and reset, we can see that our agents are all avoiding each other, and in this case they're pretty regularly spaced out. The reason that they are regularly spaced out like that is because our avoid distance and our avoid thresholds are both pretty high. If we drop the avoid distance down, remember this is the measure that determines how far away an agent is from another one before it even needs to be considered for avoiding. And then our avoid threshold, if I make our avoid distance a little bit bigger, maybe drop the world bounds a little bit, and give us a bit of tendency to our origin, and reset our sim, you can see that changing this avoid threshold is kind of what's going to be determining how far apart these agents stay throughout the simulation. And that is because that avoid threshold is what we are transforming using this value between 0 and 1. That is a function of how far away they are from each other. So a smaller value for this u avoid threshold is going to be a much smaller value or is going to result in a much smaller velocity move versus larger values which will have higher velocity moves. So you can see here that changing our parameters are really going to have a pretty big impact on the way that our overall behavior looks. There's some jittering because in this case, I believe there's probably, because our u avoid distance is like basically the same as our bounds, which is never going to be great. So you do have to make sure that you're balancing things appropriately, but this setup should give you a pretty generalizable agent-based simulation structure that you can use to add a ton of functionality and really just explore through whatever ideas you have. I'm going to stop here for today's tutorial. We're going to be using these agents as some attractors in our particle simulation later on. But for now, I think it was quite enough for today. I hope everyone was able to follow along. The project files for this will be available on Patreon for those who are Integrate Patreon supporters. As I say every time, thank you guys for supporting me very much. It's truly, one, just very motivating and gratifying that I'm able to share information and just help you guys learn and travel the same path that I'm on myself. And two, as I am no longer working full-time, being able to support myself and cover rent is also nice and frees me up to be able to make more tutorials. So thank everybody just so much again, and I will end this here. I'll talk to you guys next time.